So let's recap what we know about the normal probability distribution. In general, we're talking about continuous probability distributions. And what do we know about continuous probability distributions for random variable y? We know that we can describe the probability of a continuous random variable as the area under the curve between 2 points, and that curve is the probability distribution function. So the area under the curve, this probability distribution function, provides us the probability of the random variable taking on a value between a and b. Okay, so it was a little bit different than a discrete distribution. Here we've got this variable, or pardon me, this function on the vertical axis that doesn't really tell us a whole lot of information. Where we get the information about this random variable is with the area underneath this curve. Okay, what this curve will tell us is skewness, most likely values, and that sort of thing, but it doesn't give us a probability directly. We have to integrate finding the area under that curve between 2 points. Okay, we also said that the probability of any particular one point is 0. Okay, so let's say point C. The probability of one particular realization C is 0. And we said that's because, one, there are just an infinite number of points that lie in between any 2 points. Okay, so the probability of any one value is just 0, just because there are so many points that there can't be a probability associated with any one of those points. And then also, if we're finding the area under the curve associated with a particular point, there is no area under the curve associated with point C, for example. So the probability of a particular realization is 0. We have to find the area under the curve in between 2 points. Okay? And so now let's talk about the normal distribution in particular. We said the normal distribution for random variable y is centered at mean mu, and it has standard deviation sigma. So there are 2 parameters of this normal probability distribution: where it's centered along the horizontal axis, and then how dispersed the data are measured with standard deviation sigma. We said that the normal distribution is centered about mu. It's symmetric, and it goes off into infinity in both directions. Okay, so it goes off into positive infinity and negative infinity from the center point, mean mu. And we said that the probability distribution function, f of y, for a normal distribution is a really complicated equation. If we wanted to find the area between a and b on the y-axis, integrating this normal probability distribution function between a and b is a very difficult thing to do. We don't want to do it. Instead, what we do is we convert this normal random variable to what's called a standard normal random variable, z. Okay? So how do we describe z? It's also a normal distribution, has the same properties. However, its mean is always 0, and its standard deviation is always 1. Okay? And so what is it we're doing whenever we convert this value a on the y-axis down to a value, let's call it z sub a, on the z-axis? What is it that we're calculating here? We're using a z-score. Okay? We're converting this thing down to here with this equation, and that is how different is the value on the axis from the mean in standard deviation units. So we're saying regardless of what the unit of measure is for y, it could be in millions and billions and trillions, it could be in hundreds or thousandths or something very tiny. No matter what this is, we're converting this unit into something that we can understand a little bit better, and that is a unitless number of standard deviations away. How far away is this value from the mean? It lies this far away, calculated with this. So here, z sub a is a minus mu over sigma. How far away is this value from the mean in standard deviation units? How far away is this value from the mean in standard deviation units? Okay, so we could also convert this value b down here to the z-axis using the same formula, b minus mu over sigma. And if we wanted to find this area, that is the probability that y is between A and B, that's the same, that's the equivalent. Let's rewrite that again. The probability that y is between A and B is equivalent to this area right here. This area and this area are equivalent. That's equal to the probability that z is between z sub A and z sub B. Okay? We can go find the area associated with this curve in between values z sub A and z sub B in a z lookup table. Most times, in many different textbooks, there are many different lookup tables that could have a different appearance, but they all provide the same information. The one that we're providing in this class gives us this information. We'll go over here. On the z-axis, here's little z. The lookup table we're providing gives you this information right here. So if you go look up this particular value of little z, you'll find this area. Okay? And we can use this to describe this area here and to describe this area here. We're going to do a bunch of examples of this. It's going to make a lot more sense. But this is just an introductory picture of what the normal distribution looks like. Let's look at some examples.